Hello, everyone, and welcome to our webinar. My name is Laurie Palasse. I'm the Global Application Manager at Bruker Nano Analytics. I will be your host for this webinar, and today we are pleased to present in cooperation with Pawel Nowakowski from Fischione Instruments. We'll present you some advanced techniques to reach optimal sample preparation for large area transmission Kikuchi diffraction measurements in the SEM. And before we start, I will provide you with some housekeeping details. You should now see the introductory slide on your screen. This webinar is interactive. And you can ask questions at any time in the Q&A question answer window that you can see on the right side of your screen. The presentation will last about 40 minutes, and then we will move on to the Q&A session. If we run out of time and don't have time to answer some of the questions, we'll follow up by email. Please note that the webinar is recorded live, so it will be available soon in the coming days as on-demand version with the slides. All right. So I'd like to introduce the speakers. So I'll be the first speaker. My PhD is in structural geology and petrophysics from Utrecht University in the Netherlands. And like Pawel, my deep technical background is also a BSD. I've been working with electron microscopy and its analytics since 2 decades. I joined Bruker in 2011, and I'm now responsible for the electron microscopy analyzers applications and application scientist. Pawel holds a PhD in material sciences from Toulon University in France. Had postdocs in the Institut des Matériaux Microélectroniques Nanosciences de Provence and University of Nantes, where he was involved in multiple research projects in the field of metallurgy and nanomaterials. He left academia in 2010 to become an application scientist for a BSD manufacturer. In 2015, Pawel joined Fischione Instruments. As a senior application scientist, he provides global scientific application support for Fischione Instruments products. He's also involved with the new product development and commercialization. Pawel has published more than 30 papers in a variety of application areas and regularly presents at international conferences. The presentation is divided in 3 parts, or 2 main parts, actually. I will begin shortly by introducing the on-axis transmission Kikuchi diffraction technique and compare with EBSD and conventional TKD. Then I'll present you the main capabilities and benefits of Optimus on-axis TKD. And in the second part of this webinar, Pawel will focus on the optimal sample preparation recipes and instrumentation for large area TKD mapping. And then the webinar will end up with the live Q&A session. So remember, you can ask your questions anytime. So how is the spatial resolution for EBSD and TKD compared? So we need to keep in mind the physical spatial resolution set by the interaction volume and the effective one, which depends on the software capabilities. So I don't know if you see my mouse. Yes, you might even see 2. Okay. Okay. So keep in mind the physical spatial resolution set by the interaction volume and the effective one, which depends on the software capabilities to index correctly overlapping patterns. So for EBSD, it's quite straightforward because, well, you can almost think in only 2 dimensions since the interaction volume is very small. In TKD, we measure electron transparent samples in transmission mode. So you have overlapping patterns that are not only found at the grain boundaries, but also depends on the sample thickness, number of layers of grains, grain size, and atomic weight. So if we compare the effective spatial resolution EBSD on bulk samples, it will allow you to reach at best 20 nanometers for low kV, low prop current for relatively high atomic weight, while in transmission, the accelerating voltage is not as important as in EBSD, and with on-axis TKD, you can go down as fine as 2 nanometers spatial resolution, and maybe even better. While with off-axis TKD, so conventional TKD using a vertical scintillator, you reach a maximum of about 8 nanometers resolution. And we will see why in the next slides. So on the left is a typical EBSD geometry with a box sample at 70 degrees tilt and the vertical scintillator. In the middle is the off-axis TKD where we keep the eBSD detector head and geometry and use almost the same geometry. So you're using an electron transparent sample placed at like typically minus 15 degrees or so. So where the beams go through, and we capture scattered electron from the vertical scintillator. The intensity of the electron cloud that scatter away from the sample decreases exponentially as we move away from the optical axis, meaning as the scattering angle increases. And you can check the TEM publications to learn a bit more about that. So that's why this limitation, so you see the corresponding TKD patterns is also strongly distorted because of the mnemonic projection of the bands on the flat screen. So that also challenges your indexing. That is why Bruker and LEM3 lab at Metz in France have collaborated in providing a solution that utilizes a horizontal scintillator along with the SEM optical axis. So the geometry provides the optimum sample detector geometry to collect the signal where it's the strongest along the optical axis. And of course, you don't have distortion of the Kikuchi bands. So this detector is called Optimus, and now we have actually a second generation of Optimus, and is compatible with all our EBSD detectors except EDXS or tiny CMOS. So that allows you to simply change, so the user can simply change from EBSD to TKD detector head whenever it's needed. And the software remains the same for online, offline EBSD TKD measurements. A short example about the different geometries and the importance of speed. Here we are looking at a gold thin film of 20 nanometers deposited on an amorphous silicon nitride membrane of 5 nano. And it's a good thing that it does not require sample preparation, because here you can see the structure is very fine. On this pattern quality map, you see the pixel size is about 2 nanometers. So you need really fine step size to achieve quantitative information, because the grains and the microstructure is very fine, as you can see on this pattern quality map. So with the grain and twin boundaries here are displayed in dark gray, where there is no crystallinity or Kikuchi bands are less visible. So pattern quality value is calculated using the 6 highest intensity peaks, in the half image calculated from the Kikuchi patterns. So using the same sample, detector, microscope, KV, and probe current of about 2 nanoampere, you can see if you compare from left to right, then with the off-axis TKD, you need a longer exposure time, of course, because you don't collect the signal from where it's the strongest. And that means that you are more prone to beam instabilities. So you don't have, so this data set is clearly not reliable. It's not it's not good at all. And on the right side, you can see that you have, so using only 3 milliseconds, you don't have beam instabilities. The grains are the grain boundaries and twin boundaries are sharp, and you have the proper, you have retained the grain shape, so you don't have any distortion, so the data is reliable. So you may ask yourself, why is it important to have more signal? So for speed, but because we always want everything, right? So we want usually to measure the finest structure for the SEM, because it's much more convenient than the TEM, and we have a large field of view. We want to reduce the measurement time, so we use the lab and our time efficiently. And we, of course, we want the best data possible for reliable data at the nanoscale. This is only possible if you collect enough signal, because high spatial resolution requires low probe current. That means that pattern quality might decrease because of the increase of noise. It requires high measurement speed at low probe current, and high indexing rate, and data reliability and quality is only possible with a good signal. So the data, the TKD data is not reliable if you start filtering it with neighboring pixels, because we are using typically a few nanometer step size. So the probability that your neighboring pixels is a different grain is considerably higher than for EBSD. So dear fellow TKD users, please refrain from using indexing software options that uses neighboring patterns to increase the indexing rate for TKD maps, not for bulk, for TKD maps, because you will affect the integrity of your data set. And for all of the reasons above, it's important so to get as much signal as possible. So a short example on the gold theme again that you just saw earlier. So here we have a step size of 3 nanometers. And so all the data sets are raw, they are not corrected, no data cleaning, no filtering. So here we have twin boundaries, twin domains that are very fine of here it's one pixel size in width. And what's important to notice is that we have a few large grains, yeah. But in fact, here we have measured, we have measured almost 2,500 grains in only one measurement without beam instabilities. And the average grain size is 91 nanometers. But if you consider the fine grains, in fact, you can see that there is, here I select only the grains that are 50 nanometers or finer. It's more than 50%, a bit more than 50% of the measurement. So you really need a very fine step size. Some capabilities, so let's review some capabilities and benefits of on-axis TKD, so Optimus. This is a picture of the eFlash FS detector retrofitted with the Optimus 2 on-axis TKD head. So the difference with the first version is that it has a silicon diode in the middle of the screen for in-situ bright field imaging, and it keeps the same 3 diodes, silicon diodes at the front. So the 4 of them make the complete Argus imaging system. So the 3 at the front allows you to have brilliant color-coded dark field images. And the middle one, so for the bright field in situ, that means that this modified design helps you to work also with in situ conditions. This was done in collaboration with Alice Fanta from DTU in Copenhagen. And of course, it's compatible with the previous detectors. So this is an example on color-coded dark field images here on the gold theme with a step size acquired with a step size of 1 nanometers. You can see it's quite sharp. So here we are in this geometry where the diodes are close to the beam. So we're using the 3 diodes, and the signal is color-coded. And here, so as you can see, we're using only 800 picoampere for the signal, of course, because we're on the highest resolution possible, even if it's just qualitative. It's help us in many aspects, these images. And here is an example on a ruthenium thin film, where we can see so the color-coded dark field here compared with the bright field here on the right. So using the 3 diodes versus the single diode in the measurement position. So these images provide you qualitative characterization of the microstructure, helps you to find the area of interest, assess the sample preparation quality that we will review with Pawel later, and also alignment of the beam. That is very important. So if it's sharp, it's promising for your measurement. It's the same way as for EPSD measurement. And here is another example on a different type of sample of stainless steel, so large area here, where we can see network of dislocation and inclined boundaries that you might have seen from our previous presentation. The benefit of the diode in the middle is that we can use it in combination with other software options like max yield. Max yield is, so we use any kind of images. So here we use the Argus image to either dark field or bright field. You could even use the SE images also. So you can use this image to locate the nanoparticles by binarizing the image. And this way the software will only measure the sparse particles, and you don't need to manually select them all. So this is great, so you don't waste your time. And you can also use the diode for drift correction if you want. This is an example of the use of the max yield software option on quantum dots. So here is the IPF map. That's the images used to select the mask. And this software option, of course, you can use it with other analytical techniques like EDS, and not only in the SEM, but of course in the TEM. The software option time resolve measurements is also using the middle diode. So we use it to automatically acquire images during in situ experiment. So the TRM software options allow you to set automatic image collection and measurement acquisition according to the intervals of your experiment. So you set it up and it does it automatically, consecutively. So the software option is available for TEM and EDS and so on. And and this is an example again on the golden theme from Alice, where she was doing in situ high temperature experiments. And of course, Optimus 2 is compatible with the Bruker Hasitron Pico Indenter 89, so you don't need to retract the detector every time. It can stay in place. Another software option that is important for TKD for some microscopes, you need in order to reach higher spatial resolution, you might need to use strong magnetic field. And this is to minimize the focal length of the optical system, so to cluster the electron around the optical axis. So when using this mode, you can see on the top pattern that the Kikuchi bands are strongly distorted because the electron trajectories are affected by the magnetic field, challenging the indexing. And second, that the signal captured by the photo screen is smaller as the other patterns. So because the electrons are clustered around the optical axis of the SEM. So meaning that with a vertical scintillator, it's even more challenging, and it probably requires you to bring the screen even much closer. So this would be about 10 millimeter from the sample. So using our software option, you can see that when we correct the distorted bands, we correct the distorted band so it fits as much as possible the field-free pattern, allowing you to do quantitative measurements under this condition. And here is an example, as an application example using this software option done by Alice at DTU. So you can see that the same area is measured, again on the Goldstein team, same area is measured without the magnetic field and with the magnetic, without the magnetic field at the top and with the magnetic field underneath. So you can see that without using the magnetic field, you don't reach the spatial resolution of 3 nanometers, while with the magnetic field and the distortion correction, you can efficiently measure the finest grains and get proper, reliable data and quantitative data. A few other application examples. For the first one, I use combined EDS TKD measurement, so using the EDS flat quad detector, using the configuration as you can see here on the left, where the sample is kind of sandwiched between the flat quad and the Optimus TKD, to allow you simultaneous EDS and TKD measurement and helping you with phase identification by combining the signal. So the sample is a 6 solar cell, where here you can see the different layers, and here the corresponding IPF maps. So again, typical condition, very low probe current, so below 2 nanoampere, good speed and high low pattern quality. I mean, it's typically 160 by 120 and a large map. And here I extracted the patterns, the index patterns from the measurement. So you can see the resolution that I've used, and that the indexing is pretty good. So you can see that some might be thicker or heavier than others, and it's not a problem to index at the same time different atomic weight and or thickness to some extent. And this is the corresponding IPF map. And here you can see that we have a very high indexing rate on the 6. The last example is a thin film, again, easy to prepare. So we have here a step size of 5 nanometers, with a very fast speed. So in this single measurement of 28 minutes, we have more than 9,000 grains measured in a single measurement. So with average grain size of 70 nanometers. And what's important here to remember is it's a thin film, so it's easy to prepare. And now Pawel will explain to us how we can effectively prepare sample for large area mapping of fib lamellas. So I'm done with my presentation. Some takeaway messages. So you've seen the importance of collecting the strongest signal for achieving the finest effective spatial resolution and the different software options that can help you with that, but especially Optimus Head. And yes, and the Optimus 2 to allow you to to have in situ experiment with TKD using the drift corrections and so on. And now I leave it to Pawel, who will present to us the optimal sample preparation for large area TKD and the instrumentation. Thank you.
Hello, everybody. Thank you, Laurie, for that excellent presentation. And now I will focus on optimal sample presentation for large area transmission Kikuchi diffraction analysis, as Laurie mentioned earlier. So nowadays, the focus ion beam is mostly used for a transparent electron transparent sample preparation, either for TEM application or TKD. Now it's very responding technique, and everybody want to use it. But as any technique, FIB has some disadvantages, which is amorphization and gallium implantation of your sample. Gallium or FIB milling can introduce structural damage to your sample, and also the control of sample thickness can be relatively complex and time-consuming. So some disadvantages of the FIB here, as you can see here, the lamella is nicely bent. So this is due to excessive FIB thinning. So we want to get the lamella as thin as possible, but at some point, especially for the alloys and metal samples, the lamella start to bending at some point, and it's not anymore good for TKD and even TEM observation. To avoid those problems, we can use some kind of window milling, as you can see here on that image, but this will restrict your future area available for TKD application. And also most of the standard prepared lift out FIB samples are thin in the front and thicker in the back, which can be very nice for a TEM observation if you need high resolution for a relatively small area. But those situations are not ideal for large area TKD acquisition. Another disadvantages of the FIB is introduction of the structural damage to your sample. As you can see here, there is FIB-induced amorphization and ion implantation, and also, which is very nice, can be very easily observed in case of austenitic steel. The FIB milling introduces enough atom in displacement in material during milling that in case, for instance, austenitic steel can induce strain phase transformation of austenitic to martensite, as you can see here, different the zone exposed and the same dose of gallium milling at different voltages, as you can see here, and even as voltage as low as 1 kiloelectronvolts introduce huge damage to your sample structure. So there is a very nice paper which talk about that, and they demonstrate, the authors demonstrated that gallium ions can penetrate austenite up to 300 nanometers depending on grain structure orientation. So even if you nicely focus on this area here, the area exposed at 1 kiloelectronvolt FIB, you can see that the gallium penetration cause damage in the sample structure by creating atom displacement, and the area affected by field milling has the EBSD pattern poor quality. As you can see here, you can observe the pattern overlapping and band shift. But the area which are not affected by gallium milling, you can see has excellent pattern quality. And as you can see here, this area are not affected by any strain. I have to say that this sample before exposure to the gallium fib milling was prepared using our model 1061 broad ion beam system for bulk sample preparation. So as you can see here, the argon doesn't affect your sample structure as do gallium. So it's evident that we need a sample technique that allows us to preserve the native state of the sample structure during preparation, of course, after preparation, for accurate materials characterization using different microscope techniques. For that reason, at Fischione Instruments, we developed a model 1040 NanoMill specimen preparation system for post-FIB sample preparation. This instrument is then allowed, as you can see here, and by application of low ion beam energies a current, allow us to improve FIB prepared specimen for any electron microscopy applications. So how it works? So you can see here inside view of the chamber of the NanoMill, which is fitted with the high-end argon ion source in here, and we have secondary electron detector that allow us visuality of sample, and sample is sitting on the stage here on the special holder. The sample can be milled using low energy down to even 50 electron volts and low beam current. And tinning can be done from the front, as you can see here, or from the back, pure lamella, with the milling angles up to 30 degrees. The sample can be observed using induced electron, a secondary electron. As you can see here, we can nicely see our TEM grid with the lamella attached on the side here. The lamella can be targeted using the raster box, and then using micro-size argon beam, the gallium implantation and amorphization can be easily removed, and you can easily control the sample thickness, as you can see of here on this TEM example, is before and after nanomilling. So now I will move to the use of nanomilling system for large area TKD sample preparation. So here you have the workflow that we develop in our lab. So we start with standard lift out of lamella. This is standard preparation fib that everybody knows. And then that lamella we will wedge shape with the fib using the high angle. So we create the lamella that is thick in the front and thin in the back, and we, in that way also will preserve the protective PT cap. As you can see here from that TKD quality map, the lamella is thicker in the front than in the back. Then lamella will be moved to the nanomill system where it will be backside thinning at high angle up to 30 degrees to achieve desired thickness of lamella. Of course, depend of the grain size here. And the cap, PT cap, will be still preserved because with backside milling, as you can see here on that TKD pattern quality map, we obtain the uniform thickness across whole lamella. So once again, as you can see here from that images from NanoMill, the sample, it's milled from backside using low energy, low beam current. The sample is milled from backside. So this is backside of the grid that you can see here. The region of interest or lamella is targeted by the raster box dimension of 10 by 3 microns, and sample is tilted between 15 and 30 degrees for those operations. So how this preparation compare with standard FIB sample preparation? So here we have an example of highly deformed nickel alloy. It's a cold rolled material where total sheet thickness was reduced by 95%. So as you can see here, you have sample preparation finish at 5 kilo electron-volt FIB. It's a standard preparation, so you can see nicely here that only the front of the lamella is good enough for accurate TKD preparation. The rest is pretty thick, and also it's not pretty thick, but it's still not thin enough. And also you have to remember that you deal here with the highly deformed structure, so you need very nice sample preparation to get signal from this deformed, highly deformed grains, as you can observe here, even if those grain size is about 100-150 nanometers in average. So if you do the sample preparation using our backside high angle nano milling, you can see here that you observe very clean data from acquisition using TKD. Sample has very uniform thickness. As you can see here, this is TKD, IPF map overlap the pattern quality map. You can obtain very high indexing. The lamella is uniform over entire area. As you can see here, you can acquire the nice data from whole area with nice indexing rate, small step size, and now when you have one view on your sample, you can zoom a different area, collect beautiful Argus images, as you can see here, that field electron contrast image, and starting to correlate the defect that you can observe of the electron image with the kernel average misorientation TKD measurement, as you can see here on the right. So this is an example of the high deformed material with relatively a big grain size. The average is between 100 and 150 nanometers. I'm saying it is a relatively easy sample. It's deformed, that for sure, so demand nice preparation, but the grain size is pretty big. But what happens if you have truly nanostructured sample, as you can see here? Here we have nanostructured nickel alloy with the grain size significantly less than 50 nanometers. So as you can observe here on the TKD pattern quality map, only the large grain size can be observed. You have good signal from these large grains larger than 100 nanometers, and then those can be fully indexed. The small grains in between are difficult to distinguish. So what happens in the sample? It's what goes wrong? Why this FIB preparation, even a 5 kV, is not good enough to get good TKD measurements? So let's see the optimum sample thickness for TKD measurements. So as you can see here, if you look at the front of the lamella, and this is front side traditional FIB sample preparation, there will be not enough the material that Kikuchi diffraction occurs. Then if you go to the zone in the thickness between 10 and 20 nanometers, we start to see some patterns. We have Kikuchi diffraction, but there is not enough bands and zone axis to make accurate indexing. And for that particular sample with such small grain size, the range of thickness between 20 and 50 nanometers, you can see here we have nice patterns with a lot of zone axis and a lot of bands, and these patterns are very good for indexing. And if you go to the thicker area of the sample, you can see that the pattern quality decreases very much, and we start to see overlaps of the pattern. So the conclusion here is that the sample thickness of maximum of 3 grains layers is ideal for accurate TKD measurement. But the question that I will ask you now, if only the sample thickness matter. So if you closely look at your sample prepared by FIB, you can do, for instance, an EDS measurement, and you can see that you can observe the nice peak from the gallium on your sample. So this will indicate that you have the gallium FIB induced structural damage. And this damage will extremely attenuate the signal for TKD measurement. And if you use the NanoMill sample preparation at ultra low energy, as you can see here, 500 eV, that gallium peak will completely disappear. So there is no more gallium FIB induced structural damage in your sample. So it's not only thickness that matter. The thin lamella must be also free from structural damage. So now, after nanomilling, our nanostructured nickel alloy can look like that. As you can see here from TKD pattern quality map, you can nicely distinguish all these very small grains here, and that will allow you to fully index this area. And if you look closer, you will see that there is a lot of sigma 3 twin boundaries that are lower than 10 nanometers, as you can observe this zoom in image here with the twin of 8 nanometer width. So if you apply to that sample our workflow of backside high angle milling using NanoMill, then you can able to achieve the large area. For large area acquisition, you can using TKD. As you can see here, you have a lot of grain, large area, and you can calculate it. A true average grain size for that sample is 30 nanometers calculated over almost 6,000 grains. So it's a lot of grains, a lot of statistics. And there is 70% of sigma 3 twin boundaries that are lower than 10 nanometers. So with that, I will finish my presentation and we'll move to the conclusions. So we presented a new approach for large area electron transparent sample preparation for TKD measurement that allow you significantly reduce the FIB milling time, remove the FIB induced structural damage, control sample thickness, and improve overall TKD signal and indexing rate. So accurate sample preparation makes TKD analysis easier and provides improved results. Thank you very much for your attention.
Thank you, Pawel, for this great informative presentation. We will start our Q&A session. So a quick reminder, you can submit a question by entering it into the recording window, Q&A window on the right side of your screen, and press submit. And so we have already had a few questions, but please do not hesitate to ask more questions. The first question will be, is plasma cleaning useful for TKD? So actually, I just made 2 slides from your questions during the live. So plasma cleaning is a must to consider when before your TKD measurements. So this is an example on the same easy peasy gold thin film. So on the left, you can see without plasma cleaning prior to the measurement, and on the right, with only 15 minutes plasma cleaning prior to the TKD measurement. So it's the same condition, step size of 1.6 nanometers, 30 kV, working distance 5, very low probe current, like 1.6 or 1.7 nanoampere, so typical conditions. And you can see that, so as usual, no cleaning of the data. As you can see between with plasma cleaning or without plasma cleaning, you almost double the indexing rate. So it's considerably different. So you need to keep your sample clean, your chamber clean, the SEM chamber clean especially, and you can also plasma clean the detector head, so just the TKD with the screen, so you can clean it all together. The sample itself after preparation is still clean, of course, but the chamber is more critical. The question was, what determines the final TKD specimen thickness?
So the critical parameter, the first critical parameter, is the grain size. So you need the sample thickness maximum of 3 layers of grains, and then sample must be free of any damage created on any sample preparation that you use for a sample preparation. For instance, in the FIB, you have to remove the gallium implantation, which damage structure of your sample by creating an atom displacement and vacancy that will attenuate your TKD signal. So first the grain size, and then if you use FIB, the FIB damage. That will define your final TKD sample thickness.
Okay, thank you. One of you asked me to share some comparison of spatial resolution between on-axis and off-axis in the map. So I just prepared a slide, so it's not very nice looking because it was really quick. So on the left, you can see off-axis measurement. I'm trying to get the best measurement on the stainless steel that you saw the image earlier, and the gold thin film versus on the right the on-axis results. So it's 10 nanometers for the stainless steel and 2 nanometers for the gold thin film. So you can see that the data, the indexing is not as good. You can see the grain boundaries, and that's very important when you think about the effective spatial resolution. Is are your grain boundaries and twin boundaries sharp on the pattern quality map? Especially on the pattern. So here the pattern quality map is underneath the IPF, and here you see you are prone to beam instabilities, to drift, and that's why the grain shape is not respected. And the indexing also is not of great quality, so it's not sharp. You don't reach the spatial resolution, so that's very important. So we discussed about sample thickness, layers of grains, and the signal to keep in mind. Okay, next question, Pawel. Can we remove gallium damage from FIB lamellas using broad argon ion beam milling?
This is not the yes. This is a very interesting question. I know there is some attempt to doing that using broad argon ion beam system on the TEM sample, but the risk here is that you can redeposit the material for your grid on your sample, and then have even worse than only the gallium implantation and gallium structural damage. So redeposition is very bad for TKD sample measurements. Using NanoMill, you can only and precisely target area that you want to thin down using argon ion milling, and the beam is not static like in the broad argon ion beam milling. The beam is much smaller, it's micron size beam, and the beam will scan your sample only in your defined raster box that you put only on over your sample. So no redeposition, only sample cleaning using NanoMill.
Thank you, Pawel. There are quite a few questions for you. Do you want to pick up another one?
Yes, why not? This nice question I can see here. That we stand that we reduce the FIB milling time. Can we remind us how much time total thin film preparation would take using FIB plus NanoMill process. So yes, we reduce the milling time because what is in our approach is that we'll not have to spend crazy time to finish our sample using FIB. We will keep it a little bit thick, around 100 nanometers, in order to be able to remove all damage and not damage the sample across whole thickness. So if you over thin sample using FIB, you will have to sweat a lot, have the very experienced user, and your sample might also bend, and then you will have to start over. So you will lose a lot of time. If you keep your sample thicker, and then you will have also your PT cap, protective PT cap on the top will not consume using FIB. Then you put to NanoMill, and you can within 20 minutes, well, I mean 10 minutes for one side and another side, significantly remove the sample, diminish the sample thickness. So what is the total time is depends on your FIB skill. I mean, you know, as I don't know how fast you will lift out the lamella and then transfer to the grid and then to the NanoMill, but significantly you will reduce your time spent on the FIB if you will have a NanoMill in your lab.
Thank you, Pawel. So I have another question for myself, but maybe go ahead for one more, at least for you, because there are many questions in the Q&A. Maybe pick up another question for you. Some are asking about the NanoMill steps, and yeah, I don't know. There are quite a few questions on that.
Yeah, I'm looking at them now.
Someone is asking me if the indexing procedure for TKD is the same as for eBSD. So the answer is yes, the software remains the same. It's just that on the software, we have an option that tells the Esprit software that we have the horizontal full screen, so that the pattern center position is in around 0.5 for X and Y, which is very different from eBSD. So that's just the checkbox to inform the software that we have a very different geometry. And this is it. Everything else remains the same for the user. So it's very simple. Oh, and actually, that's also a mixed question. So help yourself with one. We have only 2 minutes left, so we will have to answer many of these questions also offline, or we do another round of Q&A another day with everyone. Thank you so much for your questions. Non-conductive samples with TKD, yes, it's possible, or non-conductive or beam sensitive. You can, so TKD, on axis TKD uses very low probe current. So 1 nanoampere is possible, definitely. You saw most of my examples are like around 1.5, 2 maximum. But you, of course, the KV will depend on the atomic weight and thickness of the sample. That also is some of the questions similar to some of other questions. So you can use TKD, on axis TKD, you can do measurements from, well, I haven't tested the real limit, but I have done some measurements, definitely measurements at around 10, 12 kV and low probe current. So depending on the beam sensitivity or atomic weight and thickness and grain size, only with on-axis geometry, of course, you can make that possible. Pawel, do you want to?
Yes, I have one nice question.
Go ahead.
What sample configuration can be used in the NanoMill, especially if an APT tips can be cleaned up using NanoMill, because we are doing a lot of TKD on the APT tips before we put them to the for the APT acquisition. Okay, yes, you can do different sample configuration in situ and ex situ, also 3 millimeter disc with the perforation in the center, and of course APT tips can be cleaned up using the NanoMill, and we have a lot of application for that. We do also TKD on those tips, and my colleague Cecily is an expert in the APT sample preparation in our facility in Fischione Instruments. So yes, of course, we can do APT tips as well.
Thank you, Pawel. A quick question for me that I had time to set up in the meantime. Someone is asking me if Optimus is compatible with all SEMs, even 5 years old. So yes, Optimus is compatible with so all type of SEM manufacturers. Better to use fake SEMs, but of course, if you have Lab 6 or tungsten SEM, it's also possible. And so old or new ones, it's just the adapter, the flange that will change. And we have also a different type of holders, so you can have several samples together, mounted together, and you have different adapters for the different stage. So that was a very good question. And we also have a mask to allow a simultaneous EDS TKD, so that you can avoid getting the background signal in the EDS spectrum. Pawel, I don't know, we have maybe time for one quick short question for you?
Yes, I have one
thank you.
short, very nice question I can see here about plasma cleaning and what kind of sample can be plasma clean. And if this is important, yes, it's very important to plasma clean the samples, and any samples can be sample can be cleaned using plasma cleaning, and we have the external plasma cleaning model 1070 that accept the TEM holders and also bulk sample, and you can put whole TKD like Laurie just shown on a previous slide, whole TKD holder with the sample to the plasma cleaner chamber, clean everything, clean the sample and holder, put it into the SEM, and then you can reuse your TKD sample as much as you can. Or if you want, and remember, I know you have the plasma cleaner or your SEM chamber, so keep your chamber, SEM chamber clean, but your sample cleaner.
Thank you, Pawel. Yeah, thanks a lot. We have run out of time, so we'll end our question and answer session. Thanks again for being with us today. We hope to have you with us at future webinars. And thanks again, Pawel, for your time.
Thank you very much.
Bye, everyone.
Thank you very much.